We will be doing problems from chapter 2, section 6, continuity. We're covering 53, 71, 79, and 85. Here we go with number 53. So we want the limit as x approaches pi over 2 from the left. And we have this function. So to find the limit of the top, you have to realize that 1 is a polynomial, therefore we know it's continuous. Sine is sine we know is continuous because we have the theorem. And then we know if we add two continuous functions, that function will be continuous. So we know the top is continuous. And if you want to find the limit of a continuous function, because of the definition of continuity, the limit must equal the value at the point. So the top would just be 1 plus sine pi over 2, which is 2. Now the bottom, we know that cosine is also continuous. That's given the theorem. But the cosine of pi over 2 comes out to be 0. Now, you should know this from section 2.4. That, by definition, we're going to say is infinite. So the answer is going to be infinite. But you got to be careful. Now, this statement here, as I say over and over, is not correct. The bottom is approaching 0, but that doesn't mean it equals this because you're not allowed to divide by 0. This statement here is undefined. So just a reminder, you don't want to write that. That's to show you my thinking in my head. Now we have to figure out if it's positive infinity or negative infinity. And here's where the unit circle comes into play. So I'm going to jump to a different app here. Let me go to this, and we're going to do Desmos. Let me log in here. All right. So we're doing the cosine at pi over 2, and some things to remember. Here in the unit circle, it's very important that you know what cosine represents. I don't have my mouse working right now. So sorry about this. I got to reconnect my mouse. I thought it was connected, but clearly it's not. All right, there we go. So back. So in a unit circle, the radius is 1. The length of this side is the cosine. Pi over 2 is up here. So as I approach pi over 2 from the left, okay, here's where it gets confusing. To the left of pi over 2 in the number line is less than pi over 2. Here, the angle is less than pi over 2. On this side, the angle is greater than pi over 2. So if we're approaching pi over 2 from the left, it's going to be on this side. So as you can see, as I get closer and closer to pi over 2, the adjacent side, that red line, which is the cosine, gets smaller and smaller, and it is approaching 0. So we know the denominator approaches 0, but cosine is that x coordinate there, and x coordinate is positive on the right side. So therefore, it's going to be positive. So the denominator is approaching 0 from positive values, therefore it's going to be positive infinity. And I'm going to erase this because that's an incorrect statement there. And that's how you do number 53. We're going to jump to number 71. So number 71, let me flip the page here. It's going to use the same properties that we've been using before and the same rules. Oh, you know what? 53, I forgot to do the other part, huh? We got to approach 4 pi over 3. So let me do that one real quickly for you guys. So we want the limit as x approaches 4 pi over 3. Now we already said the numerator is continuous and the denominator is continuous. So to find a limit of a continuous function, you just plug it in. So it's going to be 1 plus sine of 4 pi over 3 and cosine of 4 pi over 3. And we learned the limit, or actually we learned a continuous function divided by a continuous function. That will also be continuous. So that is continuous as long as the denominator is not 0 and 4 pi over 3 is not 0. So this is how we find the limit. The sine of 4 pi over 3 is going to be negative radical 3 over 2. And the cosine of 4 pi over 3 will be negative 1/2. And then, to make this pretty, we will multiply by 1, which looks like that. And so if we distribute, we're going to get 2 minus radical 3. And the bottom, negative 1. Now if we could multiply top and bottom by negative 1 or just divide by negative 1. You'll get radical 3 minus 2 as your answer. And that's the second part of 53. All right. Now we're going to jump to the next question. So this will be number 71. So some of the rules we learned earlier in this chapter are going to come into play here. So that's why it's important to know everything. X is going to approach pi. And what's going to happen, if you plug in pi in the top and plug in pi in the bottom, you're going to end up with 0 over 0. My question, do I say that equals 0 over 0? No, you shouldn't. That's an incorrect statement. It approaches 0 over 0, does not equal 0 over 0. And remember, when it's 0 over 0, that's called what? Hopefully you said indeterminate. So what did we do a few sections ago when we had indeterminate? Well, we had two techniques to deal with that, factoring and canceling or multiplying by the conjugate. Well, there is not going to be multiplying by the conjugate because there isn't a conjugate. So we're going to try to factor and cancel this. So here's where some of your algebra skills need to come into play. Now, some of you would look at this and say, I can't factor that. There's cosines there. Well, this is exactly the same as this, which is factorable. Let me show you why. It's going to be x plus 2, x plus 1. And to show where everything comes from, when you multiply those two, you get the first term. When you multiply these two, it gives you the last term. And the middle term comes from, I call the nose and the mouth. I don't know if you see the face there. So this is 2x, that's 1x. And if you add those up, you get your middle term. Now the exact same thing happens for the cosine. The only difference, instead of x, you have cos x plus 2 plus 1. Now this is why it works. When you distribute these two, you get cos squared. When you distribute these two, you get 2. And we take a look at the nose and the mouth, that's 2 cos x. That's cos x. If you add those, you get 3 cos x. So that works exactly the same with, whoa, I didn't mean to do that. Exactly the same with cosines as it does with plain x's. So the technique you would use when you have that is just treat your cosines just like they were x's. So that's the factored form. So let me rewrite that. We're going to get cos x plus 1. I'll do 2. Keep it same as how I factored earlier. plus 1. And then you're happy because hopefully you see it. We have something that cancels, and now we can find the limit of the top. And the top is continuous, cos is continuous, 2 is continuous, and if you add those, it's continuous. So how do you find the limit of a continuous function? You just find the value at the point. So it's cos pi plus 2, that's negative 1 plus 2, and that's going to be 1. There is number 71. All right, 2 more to go. So we're going to do number 79. All right, 79 requires you to know and understand the ln function. We're approaching 1 from the left. And for fun, as a bonus, we're going to approach 1 from the right so you can see what's going on here. So for this first one, x is a polynomial on top. That is continuous. And we learned ln are continuous on its domain. That's going to be important. So the domain of ln of x, you should know, is x greater than 0 because the ln function looks like that kinda. It only exists to the right of 0. So important to note that. All right, so to find the limit of a continuous function divided by a continuous function, that makes that continuous as long as the denominator is not 0. Let's see what happens. On top, it's 1. And you should know ln of 1 is 0, so the bottom approaches 0. That's going to be infinity. It's undefined. It's going to be infinity. Again, I keep on saying this so you don't make the mistake. Do not write this down. Not true. The bottom does approach 0, but it does not equal 1 over 0. 1 over 0 is undefined. All right, so let's continue going here. What does the ln function look like? So this is something that you have to just know. It's got to be part of your math vocabulary in a sense. So you should know ln looks like that. So what are we doing? We're approaching 1 from the left. Well, as I approach 1, here's 1 right there. From the left, it looks like the y value is approaching 0, which is correct. But what are the y values down here? Below the x-axis, y's are negative. So this is approaching from negative values, making negative infinity. And then on top, a similar situation is happening, down below. Now we're approaching from the right. Well, if I approach 1 from the right, it looks like the y value is approaching 0, which it is. But on top, these are positive values. So you're approaching 0 from positive values. I should put that here, not there, in a wrong spot. You're approaching from positive values, therefore, a positive divided by positive is positive. So I put positive infinity. I'm going to erase this again because technically I shouldn't have that there. And that's it. That's number 79. Let's take a look at 85. This 85 is like really important. It's checking to see if you know how to use the definition of continuity. So that's what we're going to do right now. 85. Here we go with number 85. So a few things. They want to determine the value for which A is continuous, or G is continuous, from the left, from the right. I'm going to do all this at once. We'll deal with it as one problem. So we're taking the function g of x equals, and piecewise functions, I've told you this before, you have to understand them. If you are confused about them, it's going to cost you a lot of questions. So spend the time processing through and understanding continuous functions. And this is x greater than 1. So we want to check the continuity of the function at a, actually at 1. Is it continuous at 1? So by the definition, we have to do this. The limit as x approaches, I don't know where that came from. x approaches 1 from the left of g of x. Well, how do you find that? Which function do you use? So we're approaching from the left. That's where x is less than 1. So here's where x is less than 1, so it's going to be that function. So we will use that one, the limit as x approaches 1 from the left of x squared plus x. Now this is a polynomial. How do you find therefore it is continuous? How do you find the limit of a continuous function? Well, by definition, a continuous function, the limit equals the value at the point. So very simply, we just plug in 1, and we get 2 as the limit from the left. All right, now we have to find the limit from the right. And again, we have to figure out which function we're going to use. Well, to the right of 1 is bigger than 1. And this says when x is bigger than 1, that is our function. So I'm going to use 3x plus 5. And 3x plus 5, this is a polynomial, therefore it's continuous. And to find the limit of a continuous function, I just plug it in. Do I have the right? I think I do. All right, so that is 8. Now, at this point, we already know it's not continuous. They're asking, is there a value of a for which it's continuous? The answer is clearly no. Here's why. To be continuous, the limit from the left must equal the limit from the right, but 2 does not equal 8. So therefore, you already know it's not continuous, and hopefully you see it's a jump discontinuity. They're not meeting at the same place. Hopefully you can see that. Now, if these were equal, remember the third thing you have to show is your function at the point. Your function at the point must equal the same as the other two. So what is g at 1? This says at 1 it equals a. So g of 1 would be a. So in order for this function to be continuous, all three of these have to be equal, and they're not. So I would say g of x is not continuous at x equals 1, and you have to give a reason, a justification, because, and I would just say this, the limit as x approaches 1 from the left of g of x does not equal the limit as x approaches 1 from the right of g of x. And that would be your conclusion. So you have to realize you need to give justifications why. You just can't say, nah, it's not continuous. You have to use your definitions, your theorems, to prove your statement, to justify your statement. So that's that, all right? That's it for today. I'll talk to you guys later.